Hello everyone, Merry Christmas. Today we're going to be talking about curvature, and as a gift to you, I'm going to share my own limited understanding of curvature, okay? So let's begin with the calculus notion of curvature. So if I let f be a function from some interval ab into the real numbers, then I can understand the curvature of the graph of f based on the second derivative, okay? So if I look at the second derivative of f, which is, the second derivative of f with respect to the variable x, okay, where I'm denoting the variable x to be this to be in the interval ab, this will encode the curvature of the graph of f. Okay, so if I graph f here, alright, so let's just say ab, and I have some function f, then essentially, well, let me draw this a little bit better. So let's draw it with a strict negative curvature. Okay, so if I look at the value of the second derivative at any point, the second derivative tells me the rate of change of the tangent line, okay? So the tangent line to this, if I fix a point on this curve, and I look at the tangent line is going to pass through the point that I've chosen and have the slope equal to the derivative of the function. Okay, so this has slope f prime of, let's say, p, where p is my point that I've chosen, okay? So the first thing to note is that this is a very local notion, okay? So it depends very locally on p. So in particular, I don't actually care about the behavior of the function when it's far away from the point p. I only care about the behavior of the function when it's really close to the point p. That's what's going to tell me the tangent line to the curve at p. Okay, so it's a local notion of slope essentially, and yeah, so it's like the local slope of this graph. Okay, and then if I look at the second derivative at this point p, I can understand actually the local curvature. Okay, so what does this mean? This means that essentially, if I look at the second derivative of this function at p, all right, the second derivative is going to be negative, and that tells me that the function, the slope of the tangent lines of the function are decreasing near p. Okay, so essentially, I have behavior locally like what I've drawn here. It kind of locally looks like a frowny face, and the graph is dipping below the tangent line nearby p. Okay, and if you can visualize this as essentially, tangent lines which have slope. If I look at the slope of this tangent line to the left of p, it's going to have greater slope, and then as I move forward across this interval, the slope is decreasing. Okay, so the rate of change of the slope is negative. And so in this way, the sign of the second derivative encodes a local curvature, and this we call negative local curvature. So the graph is locally kind of dipping or curling downwards away from the tangent line, okay? And then if I were to look at instead, let's say positive curvature, so positive curvature might look something like this locally. And so similarly, if I look at the point p, then, I have a tangent line to the curve, f prime, which has, this isn't f prime at p, but it's a line with slope f prime at p, okay? It's a tangent line to the curve, and then I can see that the positive curvature tells me that these tangent lines are increasing in slope, and so I have a behavior, a curvature, which is kind of this upwards bending of the graph, and we call that positive curvature. And so the sign of the second derivative tells you kind of the direction of the curvature, okay, so whether it's positive or negative curvature. And then the magnitude is going to tell you how much the graph is curving, okay. So if I look at two different graphs, both with positive curvature, let's look at this graph and then this graph, okay. So notice that if I compare the curvature of these two graphs, let's call this F1 and F2, then the curvature of F1 locally at this point P is going to be greater in magnitude than the curvature of F2. And you can see that because the tangent lines near P are changing slope at a faster rate. So the rate of change of the first derivative, or the rate of change of the slope of the tangent lines, is greater for F1. And that rate of change, the rate of change of the slope of the tangent lines, is the rate of change of the derivative. That's just the second derivative, okay? So this F1 has a greater second derivative than F2. And so not only can we ascertain information about the direction of the curvature, whether it's kind of frowny face down or frowny face up, we can also kind of glean information locally about how strongly the function is curving away from its tangent line, just based on the magnitude of the second derivative. Okay, so that's the calculus 1 or calculus 2 perspective, and probably calculus 1. Who really cares, anyways? It's the first perspective that you learn when you're studying these things. And I don't want to downplay it though. Just because you might learn it at an earlier class doesn't mean it's not important. It's extremely important. In fact, it's fundamental. All of the generalizations of this, of curvature, notions of curvature, are stemming from, in some way or another, the second derivative. And so understanding the calculus 1 intuition behind the second derivative is the first step, and maybe the most important step, towards building an understanding of curvature. Okay, so now let's look at a plane curve. Okay, so if I now, and I'm going to use gamma, so instead of a function from an interval into the real numbers, we now have a function from an interval into the plane R2. And so the way I can think about this is it can be some weird curve, and essentially this interval parameterizes the curve, the motion of this curve, okay? So if I write gamma of t as x of t, y of t here, then where, let's say I have some coordinate system x and y, then essentially, I put the coordinates x and y in the plane, and then I parameterize this curve. And so here's x of a, y of a, and then for each value of t here, I get a new point on the plane. Namely, so essentially you can visualize as t moves along the interval a to b, this curve is essentially getting parameterized from x of a, y of a to x of b, y of b, okay? And then here's an arbitrary point along the curve. Let's say x of t, y of t. Okay, so this is very different from the previous case because previously we also had a picture in the plane. Recall that previously we had a picture of a curve in the plane, and we wanted to understand this curve. We called it f of x, right? And the reality is that this picture is actually a little bit confusing because a lot of people, when they first learn calculus, they tend to think about the graph of the function as the function itself. So when I tell you a function, you think about, this is the function, this is its graph, right? The graph and the function are actually two very different things. So let's just take a minute to unpack this, right? Because it seems like we have the same visual representation of a plane curve in both the one-dimensional and two-dimensional case, which doesn't make sense. So where is this coming from? Well, if I think about if I have a function, what the graph of this function really is, okay? So the graph of this function really is a point on the plane x comma f of x. And so really, the graph of this function is in fact not the function itself, but a plane curve, okay? And the plane curve is a curve gamma from, let's say, A to B, here's A and B, still into R2, and it's going to send x to x comma f of x, okay? So this is just a special example of a more generalized plane curve, okay? So as it will turn out, our notion of curvature in one variable is actually going to extend nicely to a more generalized notion of curvature for an arbitrary plane curve, okay? But to do that, we need to instead of differentiating with respect to the variable x, remember before we just looked at f double prime, and this was d squared f over dx, right, dx squared. Here we can isolate our analysis to a single variable, namely the variable x, and everything depended on this variable x, okay? However, in this case, we might have some very weird x, y dependence. So x and y might not be related by a function, okay? So we might not be able to write y equals f of x for an arbitrary plane curve. As you can see here, this curve clearly doesn't pass the vertical line test. So this curve is not the graph of any function, okay? However, it is the realization of this parameterization with a new parameterization variable t. And so what we're going to have to do is use the idea of the second derivative to somehow encode the curvature, the local curvature of this plane curve, but this time using the variable t, okay? So, how is this done? Well, analogously to the one-dimensional case, we need to look at a tangent line to this curve. So let me use a different color. Okay, so we first need to figure out an equation for the tangent line to this curve. And then once we determine the equation of the tangent line, the curvature is going to measure how the plane curve bends away from the tangent line, okay? So in this case, you can see that the plane curve that I've drawn is bending, kind of bending in this direction away from the tangent line. And that act of bending is what we're going to try to encode mathematically as a curvature. So first of all, let's figure out the equation of this tangent line. Now, some of you may have seen this, but I claim that if I call this, let's say that this is a vector t, okay? And then the line is just the span of this vector. So I just basically take all scalings of the vector. I fix a tangent vector t. If I find a tangent vector t, and then I basically define a line which goes through this tangent vector, that'll be my tangent line, okay? So the tangent vector t is going to be gamma prime of t, okay? So, and now my prime is a derivative with respect to time, okay? So this is d gamma over dt. And then in coordinates, this is just x prime of t, y prime of t, okay? All right, so I apologize for using primes for derivatives. Previously, I used a prime for a derivative with respect to x when we were looking at the one-dimensional case. Now I'm using primes for derivatives with respect to t, okay? So just keep that in mind, that all of my primes here are derivatives with respect to t. Now, why is this the correct notion of the tangent line? Well, the idea for why this is the tangent line kind of stems from the same idea of just the ordinary calculus derivative. So the way that I could calculate this tangent line is first by taking a secant line, okay? So if I first take a secant line where I look at gamma of, let's say t plus some small number epsilon, and then so that here's gamma of t plus epsilon, here's gamma of t. So, yeah, I apologize. I previously wrote this point as being gamma of t, but now I'm just abusing notation and I'm saying, okay, now this is my gamma of t. Okay, so I'm abusing notation, but hopefully the intuition is clear here. So I have gamma of t, then I move out a small bit and I have small bit of time, so a small number epsilon forward in time, and so now I'm here on the curve gamma of t plus epsilon. And if I look at the slope of this line, this secant line through my plane curve, and this is just going to be gamma of t plus epsilon minus gamma of t over epsilon, okay? So why is this the case? So let's think about it in terms of x and y, right? If I think about it in terms of x and y, then I know that the slope of this secant line is just rise over run, so delta y over delta x, and so if I were to encode this, okay, so instead of encoding this as slope, delta y over delta x, I can encode this by a vector, delta x comma delta y, okay? So I can code this as a vector, delta x comma delta y, where that's precisely this secant vector, okay? And the secant vector is precisely gamma of t plus epsilon minus gamma of t. Now in coordinate notation, this is just x of t plus epsilon minus x of t. That's the x coordinate, and then the y coordinate is y of t plus epsilon minus y of t. And so this is the vector that that represents the direction of this secant line. And then I only care about the direction, so I can scale this by a constant. I'm going to scale it by epsilon, just to ensure that it doesn't go to 0. And then as I send epsilon to 0, I'm essentially bringing this, so the scaling by epsilon is just to ensure that the vector doesn't go to 0. So I can retain some information about its direction even when epsilon is small. Because if I send epsilon to 0 without dividing by epsilon, I'm just going to get 0. And you can visualize taking this vector, this is the literal vector that we've drawn, and we're trying to basically send it, we're trying to move this gamma of t plus epsilon really close to gamma of t, and when we do that, this vector is going to shrink and go to 0. So I scale by 1 over epsilon so that I can just focus on the direction of this of the secant line. And then, as I send epsilon to 0, notice that's essentially bringing the secant line closer and closer to the point itself. And then we have that the secant line will approach the tangent line in the limit as epsilon goes to 0. But notice that in the limit as epsilon goes to 0, this expression, this is just x prime of t, y prime of t. Okay? So that tells us that by basically the similar ideas as discussed in Calculus 1, we can understand the tangent line to a curve by just taking the derivative of the parameterization. Okay, so this truly is the tangent line to the curve is x prime of t, y prime of t. Okay, all right. So let me. Okay. So now that we have our tangent line, we're essentially going to look at what we want to do is we want this tangent vector to have unit length, because to understand the curvature, like I was actually explaining about the secant line, okay, to understand the curvature, we actually really just care about the direction of the tangent vector, okay? We don't care about its magnitude. And that's reflected from the fact that we don't actually care about how quickly we're like moving through this curve, okay? So let's say I defined a different parameterization of this curve where, let's say I just ran across the curve like twice as fast or something. Or maybe I like I went along this curve more slowly, and then I sped up at the last second and kind of traversed the end of the curve 3 times as fast or something. That doesn't actually change the shape of the curve, and what we're interested in is the shape. We're interested in the curvature, which is a notion of shape. And so we don't actually care about specifically how this curve is parameterized. That's the key. We just care about the shape of the resulting graph, the shape of the resulting geometric curve in the plane. Okay? So that means that I'm free to reparameterize this curve as long as it has the same geometric shape or the same graph, right? As long as it has the same graph, I can reparameterize the curve so that its tangent vector is always of magnitude 1, okay? And how do you do this? Well, the idea is you use the arc length of the curve, okay? So notice that arc length is somewhat of a geometric invariant, okay? So arc length is, in the plane, arc length is given by, essentially, if I have a small piece of a curve, ds, then I know that in the plane, ds squared is going to be dx squared plus dy squared. So this is actually a consequence of something called a Riemannian metric, which is the Euclidean metric on the plane. So the Pythagorean theorem, a lot of people think it's like provable. The Pythagorean theorem is actually just an axiom or like an additional structure that we're imposing on a plane, which gives it a flat curvature, it gives it a notion of being flat. So this is the Pythagorean formula on a differential scale, and what it tells me is that locally, if I zoom in close enough to a curve, then locally, picture like looking at this section of the curve and then zooming in super close, then we know that this infinitesimal arc length is just dx squared plus dy squared. That's just the Pythagorean formula. That's really an additional structure we're assuming to be true when we talk about a flat plane, okay? All right, so where am I going with this? Well, the idea is that we're going to use arc length to parameterize the curve. And because arc length is this kind of geometric invariant, when I parameterize the curve along arc length, so let's say for the first, let's say we parameterized it in tenths, then the first tenth of the time I would have traversed the first tenth of the total arc length. And then the next tenth of the time I would have traversed the next tenth of the total arc length. And then, etc. So basically, I'm moving along this curve, and my speed of movement is essentially chosen so that I am traversing a constant amount of arc length. Okay? So, yeah, so just picture a runner running along this track, and then in the first, let's say, 100th of the total time, he traverses the first 100th of the arc length. And the next 100th of the time, he traverses the next 100th of the arc length, etc. And clearly, this is going to give us a constant speed parameterization, because we're traversing over a fixed time the same distance every time. The same arc length is being traversed through each time interval. And so this is going to give us a constant speed parameterization of this geodesic. And that's exactly what we want. We want a constant speed parameterization of the, sorry, not geodesic, but of the curve. We want a constant speed parameterization of the curve, because then the tangent vector is going to be of the same magnitude. And so it's only changing direction. It's not changing length. And that's kind of nice, because then, if my tangent vector is always the same length, then I can kind of lock down and focus more on the way that the tangent vector is changing, is rotating, and that rotation of the tangent vector is then going to allow me to understand the curvature, okay? Okay, so let's talk about how do you create this arc length parameterization. Well, okay, so using this formula for the differential arc length, we can calculate the total arc length of a curve the total arc length of the curve is just the integral over the complete time interval AB of the of ds, the differential of the arc length. So we're basically using the integral to add up all the differential arc lengths to get the total arc length. And then by our formula for ds, the Pythagorean formula, which again is a structure that we impose on the plane called a Euclidean metric or Riemannian metric that we're putting onto the plane, then this is just the square root of dx squared plus dy squared, okay? So that's just taking the square root of this expression here. And now if I multiply and divide this expression by dt, okay? Now I should mention that a to b doesn't actually make sense here because a and b are integrations with respect to t, the parameterization t. So I really need to make sure this integral is in terms of t all the way through, because then this bound a to b makes sense, because this integral is over the parameterization variable t, right? T is the variable which is kind of parameterizing my curve through AB. So if I want to integrate from A to B, then I better be integrating against t, otherwise this integral doesn't make sense. But intuitively speaking, what I really want is ds. So we have this expression here where I multiply and divide by dt. Then if I write ds as the square root of dx squared plus dy squared, I get this expression here. And now I can bring the dt on the denominator inside the square root, okay? And that's going to make it turn into a dt squared, okay? And then I can break this over the addition symbol. So I have a dx over dt squared plus a dy over dt squared here, okay? And well, what is this expression? Well, this expression is precisely the magnitude of the derivative gamma prime, right? As we can see here, gamma prime is just x prime y prime, okay? So this is just x prime squared plus y prime squared. So let me just write this out here. So we have L is equal to the integral from a to b of square root of x prime squared plus y prime squared dt. And notice that since this is just the norm of the vector x prime y prime, so this is just the integral of a to b of the norm of gamma prime of t dt. Now let's interpret this for a moment. This is just the speed, okay, of the parameterization. So essentially, if I look at the local speed, then I'm basically saying that the speed of my parameterization over a differential time unit is going to trace out this much differential arc length, which is just the differential time unit multiplied by a scaling factor, which is the speed. That totally makes sense, because if I think about a runner running along this track, then if he's running, let's say, really quickly at the start, let's say he's running really, really fast, he's sprinting at the start of the race, then he's going to be tracing out more arc length per unit of time, right? And so the amount of arc length that he traces out per unit of time should be locally, at least, directly proportional to his speed, which is the case, his or her speed, which is the case in this integral here. So this tells me that this makes intuitive sense, and this seems like it should be the right definition of arc length, okay? So now what we're going to do is we're going to define this a new parameterization s, okay, and s of t, which is going to be the cumulative arc length from a to t. So a to t, gamma prime c dc. Okay, so where am I going with this? I don't want to erase my picture, because I'm I like to hold on to my geometric insight even when it becomes a burden to my efficiency. Okay, so anyways, So what is this expression? This is the cumulative arc length. So basically, if I look at, this is still gamma of t, this expression that I've written here, s of t, is actually just the arc length from of the curve all the way up to the point t, okay? So we can picture this arc length s of t as the arc length of the curve as I trace it out from a to t. So it's a cumulative arc length. And now notice that if my curve is regular, okay, so if it always has positive speed, which is a condition that we need to enforce, okay, so regular curve, the norm of gamma prime t is always positive. So if my curve is regular, then I know that if I take the time derivative of s of t, okay, s prime of t is just going to be the norm of gamma prime of t by the fundamental theorem of calculus. So the speed of s of t is just actually the speed of gamma, okay? And so what is this telling me? Well, this tells me that since I'm assuming my curve is parameterized with speed greater than 0, which is an important assumption actually to ensure that this plane curve is actually a regular submanifold of the plane, a one-dimensional submanifold. Then this tells me that s prime of t is always positive, and so in particular this is a strictly monotone increasing function. So by the inverse function theorem it has an inverse, okay? So the inverse function theorem tells me that s of t is invertible, and that t of s is well defined. So t of s inverse of s of t exists, okay? Okay, well this is great news because now it means that I can reparameterize my curve, reparameterize gamma of t to gamma of t of s, okay? And gamma of t of s is going to be a new curve that goes from 0 to L, where the domain is the interval 0L, where L is the total arc length of the curve into R2. And this is a unit speed curve. Okay, so in particular, one can show that that this curve, that gamma prime, not gamma prime, but d gamma over ds, okay, so with the derivative with respect to my new parameterization variable s, which is the arc length, the magnitude of this derivative is equal to 1 everywhere, okay? So why is that the case? Well, if we look at the chain rule here, if we look at the chain rule, so if I differentiate gamma of t of s with respect to s, okay, then this is going to be, by the chain rule, first take the derivative of the outside function, so this is just gamma prime of t, and then I take the derivative of the inside of the function, which is dt over ds, okay? We just calculated that that s prime of t, which is ds over dt, is equal to gamma prime of t. So look at that. Gamma prime of t is equal to, its norm is equal to ds over dt. So this is equal to, and to be really careful, I can bring the dt over ds outside of the norm here. And now I know that the norm of gamma, so the speed of gamma, well, this is precisely ds over dt, okay? By our previous calculation. And so when I multiply these two quantities together, by the inverse function theorem tells me that this quantity, the derivative of the inverse function, right? T is the inverse function that we use the inverse function theorem to garner. We use the inverse function theorem to get this t as a function of s. And not only did we get t as a function of s, but the inverse function tells us, the inverse function theorem tells us that dt over ds is the inverse of ds over dt. So in particular, dt over ds is equal to 1 over ds over dt, okay? That is, again, a direct result of the inverse function theorem. So that tells me that this value is 1. So in particular, we've just proven this result, which says that if I reparameterize according to the arc length, the cumulative arc length, then the speed of my parameterization is constant and it's equal to 1, okay? So this is a great first step because now we have a tangent vector, okay? So the norm of the tangent vector is, this is the norm of the tangent vector everywhere. So the tangent vector is of constant magnitude equal to 1, and it's only changing direction. And so now we can study the way that the direction of the tangent vector changes, and we study this in order to gain a notion of the curvature of the plane curve, okay? So now we have gamma from 0L into R2 is unit speed parameterization. And now we're going to start looking at the second derivative. So we know that gamma prime of s, okay, now my primes, I'm again abusing notation. Now that I've established this reparameterization, I'm going to go ahead and implement the reparameterization. So now everything is in terms of s. In my picture here, all my parameters are now in terms of s here, gamma of s. And I'm kind of going to ignore t for a moment, for the time being, and assume that I've already done the reparameterization completely, okay? Okay, so, all right. So making some progress here. So my tangent vector t of s is just defined to be gamma prime of s, which again is x, which is again x prime of s, y prime of s. And now I need to understand the curvature. So what I'm going to do is I'm going to look at gamma double prime of s. And as we've discussed in the previous video, but I'm going to cover it again. So gamma double prime of s is the way that the tangent is basically the rate of change of the tangent vector. Okay? So this is rate of change of t, okay? So rate of change of the tangent vector. And of course this is t prime of s. Okay? And the idea, the first thing we observe is that since the tangent vector is constant magnitude, we know that that t prime of s, so this is our first observation, that t prime of s is orthogonal to t of s for all s, okay? Why do we know this? Well, if I look at the inner product of t of s with itself, okay? So again, I'm using the Euclidean inner product, and more generally in Riemannian geometry, you're going to have an inner product on the tangent space everywhere. But here we're just using the Euclidean inner product. So recall that the inner product of two vectors, let's say x1 and v1 and v2, let's say, it's going to be v1x times v2x, so v1x is the x component of v1, times v2x, which is the x component of v2, plus v1y, v2y. And so the way that you can think about this is a matrix multiplication. You have v1x, v1y, and then I have the v2x, v2y here. And then real quickly, just because we're on the topic of Riemannian geometry, this inner product, I should really be thinking about it secretly. The inner product that we're used to is really just, so v1, v2, I really have v1x, v1y, and then I have an identity matrix sitting here in between the two vectors. v2x, v2y, okay? And so essentially, I can view this as v1 transpose times the identity matrix times v2, okay? And so this is the definition of Euclidean inner product of v1 and v2. And then to change this inner product, I can actually change the matrix I. And all of this math and all of this analysis will still work for a different inner product. As long as this matrix is symmetric and positive definite, which means it has positive eigenvalues. So the eigenvalues of this matrix need to be positive, and the matrix needs to be symmetric. As long as the matrix satisfies those two conditions, this will indeed give us an inner product on the plane, and or more generally on Rn. You could extend this to Rn. And the point is that with different inner products, you're going to have different curvatures. Okay, so this is actually called the first fundamental form. And the idea is that it's the Riemannian metric. It gives us a notion of geometry in the space because we have a notion of, it gives us a notion of length, right? The length of a vector is simply the square root of the inner product with itself, okay? So moving back to our discussion, I don't want to get too in the weeds here. If I look at the inner product of t with itself, this is the Euclidean inner product. Well, this is just the square length of t of s. So this is just t of s squared, right? Every inner product automatically gives us the geometry of our space, okay? And in particular, if I inner product a vector with itself, that's going to give me the square length of that vector, the square norm of that vector, okay? So in this case, the square norm of t is just a constant 1. This is the key, is that the length of the tangent vector is constant, is equal to 1 because of our reparameterization. And so, if I now take the derivative of this identity with respect to s, okay, then I'm going to get, by the product rule, I'm going to get t prime of s, t of s, plus t of s, t prime of s, is equal to the derivative of 1, which is a constant, so that's equal to 0. Okay, so this tells me that, well, these two are the same because the inner product is symmetric. So this is going to be the inner product of t prime of s with t of s, and then I have two copies of it, and that's equal to 0. Okay, so what that tells me is that this inner product, t prime with t of s, this is 0, which means that t prime of s is orthogonal to t of s. So the rate of change of the tangent vector, let's draw this now. The rate of change of the tangent vector, locally speaking, if I just move this tangent vector slightly along the curve, the rate of change is actually orthogonal to the tangent vector. And you can kind of think of that, you could think of that as if you just view a circle, picture a circle, okay? Let's do a circle now. So if we picture a circle, and then I look at the tangent vector to this circle, which might look something like this, okay? And now I picture moving the tangent vector just slightly along the circle. So I just consider a differential change in my point. Then the change in this tangent vector, as long as it's not changing magnitude, is actually going to be in the direction of the centripetal acceleration. Maybe you've taken physics 1, in which case you would have learned that for uniform circular motion, you have a centripetal acceleration, which is pointed towards the center of the motion. Okay, so towards the center of the radius of circular motion. Now, this centripetal acceleration is the rate of change of the tangent vector. Okay, and so notice the rate of change of the tangent vector is orthogonal to the tangent vector, and so this is kind of a local form of centripetal acceleration. Okay. All right, so hopefully that made some sense. Another way I could have drawn the vector is here, right? So if I were to move this vector, basically, okay, let me say one last thing about this. So if I consider the circle again, so really the construction that I want to consider is move the vector slightly along the circle, okay, to a new vector here, okay? But now I want to emphasize that since we're in R2, I have a nice way of transporting this vector back onto the original vector, okay? So I can just take this new vector that I've moved along my parameterization by some small time interval, and now I have a new tangent vector to the circle, and now I can just slide this tangent vector back to the original starting point in order to compare it with the tangent vector to the circle. And when I do this comparison, what I'm going to get is some difference vector as I've drawn here. So the difference between the two vectors looks like something like this. And then as I send this point closer and closer to the original starting point, so I look at the limit as this perturbation goes to 0, then it should be that this vector here, this change in the tangent vector, the vector which measures the local acceleration, should approach a vector which is orthogonal to the original tangent vector in the limit, okay? All right, so now we have this idea that t prime of s, the rate of change of the tangent vector, is orthogonal to the tangent vector, okay? Now I'm going to define a normal vector to the curve. So we're going to define n of s to be normal vector to the curve. Should just be the rotation by pi halves of the tangent vector at s. And so this is just, I'm going to apply the matrix, basically 0, -1, 1, 0, t of s. So what does this look like? Well, let's go back to our picture of a curve here. I want it to be a smooth curve. Okay, so here's gamma of s in the plane xy. And now I have, let's suppose that I have my tangent vector t to the curve. Okay. So now I'm going to rotate this tangent vector by 90 degrees counterclockwise. Okay. So I rotate this tangent vector 90 degrees counterclockwise to get the normal vector. Okay. And these should be of the same length, right? They're just rotated copies of each other. And then here's the tangent vector of s, which is gamma prime of s. And here's the normal vector, okay? And so what we've just discovered is that t prime of s, so the rate of change of the tangent vector, is orthogonal to t of s. In particular, this t prime of s is in the direction of the normal vector, okay? So notice that these two vectors the normal and the tangent vector form a frame for the plane, which means they form a coordinate basis for the plane, and they're orthogonal, so they're 90-degree angle. So that means that if t prime of s is orthogonal to t of s, this means that it's a scalar multiple of the normal vector. So t prime of s is some scalar multiple of the normal vector, and this scalar multiple is the curvature. Okay. Okay, it's we use a kappa. I think is the correct terminology for the letter. So it's kind of this K-looking letter, which is called kappa. I'm not an expert with the Greek or the Roman alphabets or whatever, but okay. So we have a notion of curvature. Now, why does this relate to what we previously understood? Well, notice that kappa is encoding the way that this curve curves towards the normal vector, okay? So in this picture that I've drawn here, okay, essentially here's the idea, is that t prime of s, since t, you can envision t changing as I move along this curve, and as t changes, it might change from something like this to something slightly like in this direction, and so t prime of s, let me draw t prime of s in a different color actually. Okay. So t prime of s is going to look something like so. And so intuitively speaking, t prime of s is going to be in the direction of this normal vector, and it's going to be pointed towards the normal vector because the curve is sort of bending towards the normal vector, okay? So in this case, in this specific case, we would have that kappa would be positive, okay? So kappa is positive, which indicates that t is bending towards the normal vector. So this means that the curve is bending towards the normal vector. And then the magnitude of kappa, similarly to before, the magnitude of kappa just tells us how much it's bending towards the normal vector. So over here where the curve is kind of flatter, okay, so maybe here, over here we have a tangent line, we have a normal vector. Here kappa is going to be smaller, right? Kappa is small. And because the curve isn't really bending very much towards the normal vector, it's almost locally flat in this region. Whereas if I go around this curve, or if I go around the bend of my plane curve, if I go around the bend of the plane curve, then in this scenario, I certainly have that the tangent vector is like sort of bending towards the normal vector more. And so in this case, kappa is going to be larger, okay? And when I say larger, I mean in magnitude, okay? So the magnitude of kappa, how large of a number it is in magnitude, is telling us how much the curve is bending away from the tangent line, okay? So bending towards the normal vector is the same thing as bending away from the tangent line. And so the larger kappa is in magnitude, the more the curve is bending away from its tangent line. And then the sign of kappa tells me how it's bending away from the tangent line. So either it's bending away from it's bending away towards this normal vector. So in this case, it's going to curve in this direction. Or if I look at earlier on the curve over here, if this is my normal vector n, and here's my tangent line, then notice I'm bending away from the normal vector at this stage of the plane curve. And so this would be kappa negative, okay? So this would be kappa negative. And so it's still going to have a large magnitude at this place because it's kind of bending quite strongly in this region, but it's bending away from the normal vector. So this is negative curvature, okay? Awesome. So we kind of get the same information as we got in the one-dimensional case, only now we're getting it in 2 dimensions, and the key ingredient that we needed was the reparameterization of the plane curve according to its arc length. Once we reparameterized the plane curve according to its arc length, then somehow we were able to garner a stronger information about the direction of change of the tangent vector, right? How the tangent vector is changing direction, because the tangent vector isn't changing magnitude. And because it isn't changing magnitude, the only thing that's changing is its direction. And so when we analyze its derivative, we're really just looking at the way that the tangent line is changing direction. And so by looking at the change of direction of the tangent line, we can understand the curvature of the plane curve, okay? So this is the first key step towards an understanding of curvature. But we're going to keep going because it's Christmas Eve. We got to keep going. We got to actually build this up further, okay? So now we're going to go to a surface, okay? And then real quick, I will mention that you could do this notion of curvature in three-dimensional space in R3 with something called the TNB frame, okay? And I'll just quickly mention that before we go on to surfaces. So, if I now have a curve, and the arc length parameterization idea is going to be the same thing in 3 dimensions, so I'm going to kind of black box the arc length reparameterization, because I already showed you how to do it in 2 dimensions, and the idea is the same in 3 dimensions. So if gamma is now a space curve, okay, and we're going to assume that we've already done the arc length reparameterization, so it's a unit speed space curve. Before we go into this, let me just mention one quick note, which is that in order to get this unit speed reparameterization, the key assumption we needed to make about our curve was that it had a positive velocity everywhere. Okay, so that's a key ingredient. Also, that's a key assumption, is that if somebody gives you a curve, in order to verify that it has this unit speed reparameterization, a sufficient condition that you can check is that its speed is everywhere non-zero. Okay, and of course it has to be a smooth curve, so it has to be differentiable up to all orders. And certainly we don't need all orders of derivatives, but for simplicity we're just going to assume smoothness, which means infinitely differentiable. Okay, so just picture a very nice and smooth curve, and this time we're working in space. Okay, so we have a curve kind of coming out of the board here in space. And now how are we going to do it for this curve? Well, it's actually kind of a similar idea. So first of all, we have the tangent vector, okay? And the tangent vector is just gamma prime of S, okay? And notice that this is always a unit vector by our assumption that this is a unit speed curve, okay? So it's an arc length parameterization. Then I'm going to define the normal vector. So here's my tangent vector to my curve, okay? Now I'm going to define the normal vector. Previously we just defined it as a counterclockwise rotation by 90 degrees, but in 3-dimensional space we don't have that flexibility because there's actually an entire plane that's orthogonal to this tangent vector, okay? There's an entire plane, so we don't have a nice way to choose the normal vector. So we're just going to define it to be gamma double prime of S normalized, so divided by its length. Okay, and so the idea is that there's no canonical way to define this normal vector, and so we're literally just going to define it to be in the direction of t prime, or in the direction of gamma double prime. Okay, so in this case my curve looks like it's kind of bending in this direction, so maybe I want to say that my normal vector might look something like this. Okay, here's n and t. Okay, so the normal vector is just the direction of how this tangent vector is, the rate of change of the tangent vector. Okay. All right, and then the last thing in our frame is called this B, this binormal vector, okay? So the binormal vector is just t cross n, okay? All right, and this is just basically encoding the fact that I want t, n, and b to form a right-handed coordinate, orthonormal coordinate frame. So by using the right-hand rule, I can point my hand in the direction of t, curl my fingers, my right hand rule, in the direction of t, curl my fingers towards the direction of n. So notice I'm curling my fingers counterclockwise because it's my right hand. And then the direction that my thumb is pointing, which is something like this direction, almost out of the board here, okay? this direction is B. Okay, so we have sort of an orthonormal coordinate frame here, and then this orthonormal coordinate frame is going to kind of sweep. It's a smoothly varying frame, which basically forms a basis for R3. It's a complete. It forms a basis for the tangent space of the surrounding manifold. Surrounding manifold is R3, and then this coordinate frame is like a smoothly varying basis. It's an orthonormal basis, and it's sort of adapted to the curve. Okay, so it's sort of like you could think of it as like the frame of reference of the curve almost, where if you're living on this curve, right? If you're like an individual who lives their entire life on this space curve, then you would probably want to live your life. If you're, of course, you're a three-dimensional being, but you're living, you're moving along this plane curve in space, then you might want to use the TNB frame, because it might make the most intuitive sense to you as you're living on this curve, and this coordinate frame is somehow adapted to the curve quite well. Okay, the reason why it's adapted is just because, again, we have the tangent vector to the curve, and then we have the normal vector, which is automatically given by gamma double prime of S. So let's stray away from this analogy of a person living on the curve, because it's a little bit confusing, and let's look at the curvature of the space curve. Okay, so the curvature of the space curve is actually just the magnitude of T prime of S. So again, T prime of S is just going to be in the direction of this normal vector, and we're going to define it to be kappa times n. Okay, so it's definitely in the direction of the normal vector, because that's how we defined the normal vector. We defined the normal vector so that this T prime of S is n is the direction of T prime of S by definition, right? Gamma double prime is just T prime of S. So T prime of S is automatically in the direction of n, and this scalar multiple, which encodes the magnitude of T prime, is again, kappa is again the curvature. Okay? Alright, and so then let me just grab these formulas that I want to emphasize here. Okay, so I just wanted to quickly emphasize some formulas. And by the way, shout out to the textbook that I'm currently studying. This is Differential Geometry by Loring 2. This is where I'm learning all this stuff from. Highly recommend the book. It's truly an excellent book. Okay, so it turns out that there are these formulas for the derivative. Okay, so if I look at TNB prime, okay, so if I take the derivative of all of these vectors, we did this actually in a previous problem. Okay, all of this was done in a previous video. I'm just kind of briefly glossing over it. If you take the derivative of this vector TNB, then you actually get a matrix of the following form. Okay. So really interesting here. We know, not only do we understand this frame, we have a nice definition for this frame, and it tells us the curvature of our plane curve, but actually we have this new constant called tau, which is the torsion, okay? And so torsion is not something that I'm as familiar with. So if any of you have a really nice geometric interpretation of the torsion, please share that with me, because I haven't done the research yet, and I'm still studying the subject. And so yeah, if any of you could figure out what's a nice geometric interpretation of the torsion, please let me know in the comments, okay? But this is a really nice formula which tells us how, a differential equation for the TNB frame. And this differential equation, you know, we have just these, it's just a constant, right? It's a linear system of differential equations, right? This is a linear matrix because all of these tau and kappas, I guess these are changing with the, right? These do depend on S, right? All of these parameters do depend on S. So it's actually not a fully linear equation. I apologize. Yeah, it's not a linear equation, but it has a really nice, if we look at just, you know, fix a point S, then it is a really nice linear equation which relates the local derivatives t of S, n of S, and b of S, their derivative, this prime is d over ds, to the original TNB frame. Okay, so that's just a little bit about TNB frames. Now let's move on to surfaces, okay? All right, so this is where things get really quite interesting, okay? So how should I say this? Okay, let M be a subset of R3 be a surface, okay? So let's just draw a picture here. Okay, so we have some surface. Now, I want to understand the curvature of this surface. And locally speaking, okay, so we actually want this to be what's called a regular surface. And then the idea is that if you've taken manifolds, then locally this surface is of the form, even if you haven't taken manifolds, still understand this. So locally, what we want is that our surface is the zero set of some equation. So locally, M is the zero set of a regular function. Regular meaning derivative non-zero. Okay, so let me just do an example of what I mean by this, so that if you haven't taken manifolds or you're not familiar with what a regular surface is, you can also just follow along. So let's just do an example of a sphere, okay? So a sphere is given by the equation x squared plus y squared plus z squared is equal to 1, okay? And, sorry. Okay, well, this the coordinates are actually going to be centered here, x, y, z, inside the sphere. Okay, so what this is it's a function f from R3 into R. And my function is basically, I want to send x, y, z into x squared plus y squared plus z squared minus 1, okay? And then, so this is a function from R3 into R, and the idea is that if I look at its derivative, df, okay, so its derivative is going to be essentially the partial f of essentially the gradient of the function, in this case. And so it's just going to be 2x, 2y, and 2z, okay? And notice that this is non-zero when x squared plus y squared plus z squared is equal to 1, okay? So on the surface of the sphere of radius 1, this derivative is non-vanishing, so we call this function regular, okay? So, and then the idea is that is that if I look at the image of this function and I look at, okay, all the points that get mapped to 0. So I look at all the points that get mapped to 0. That's just f inverse of 0, okay? So this is equal to the set of points x, y, z and R3 such that f of x, y, z is equal to 0. Okay, but f of x, y being equal to 0 is the same thing as saying that, that x squared plus y squared plus z squared minus 1 is equal to 0, which tells me that these are exactly the points which satisfy this equation, x squared plus y squared plus z squared is equal to 1. So namely, the level set of 0 of this function is just the sphere, okay? And then since every point on this level set, okay, so every point of f inverse 0 is a regular point, which means that the derivative of f, or the differential of f, is surjective, okay? So it's non-zero, and it's more generally, it's surjective at every point in this level set. That tells us that by the regular value theorem, f inverse of 0 is actually a submanifold, embedded submanifold. Okay? And so these are the types of manifolds we want to consider, because these are the types of manifolds where we can understand their local properties through understanding, like they inherit the geometry of R3. Essentially, the reason why we care about these types of embedded submanifolds, or these types of surfaces, is because we know how to do geometry on R3 on the ambient space. And then if we have an embedded submanifold, essentially we can use the Euclidean metric. So the Euclidean metric on R3, which is our inner product, our canonical inner product of two vectors. And that canonical inner product will restrict to the submanifold. Okay, so the submanifold, because it's an embedded submanifold, it's going to inherit the geometry of R3 through the restriction of the inner product. Okay? And so this is the key. This is the key condition that we need to assume about our surface. So now, when we have this surface, we want to understand its curvature. The way that this is done is through the normal vector to the surface. Okay? So, what we do is, because it's a regular surface, it's locally the zero set of some function. And in particular, I can choose a coordinate patch and find a local normal vector field, okay? So the normal vectors are just essentially going to be, if this is the level set of some function, then the normal vectors are going to be the gradient of that function, okay? So let me just emphasize this. So the normal vector of the surface, let me just say, before we go into this, again, why are we considering the normal vector of the surface? The normal vector of the surface is kind of going to tell us how the normal vector changes along the surface is going to encode information about the curvature of this surface. Okay, so that's where we're going with this. Now, okay, so, but I can't just define a normal vector at a single point. I need a normal vector field, a local normal vector field to the surface, okay? And this is where the regular surface comes in, okay? Because if m is the zero set of a regular function, then I have that m is like f inverse of 0, where f is some function from R3 into R. And of course, f inverse of 0 is a set of regular points, as we previously discussed. And then so m is equal to f inverse of 0, maybe locally, not necessarily globally. In the example of a sphere, that was a global level set, right? The sphere is a global level set of some regular function, but we don't, in general, we just need it to be locally the zero set of a regular function. And then what we can identify is that the gradient of f, okay? So the gradient of f is going to be orthogonal to m, okay? And why is it orthogonal to m? Well, the gradient of f is the direction in which f is changing the most. Okay? But f does not change along m. F is identically equal to 0 along m. Okay? So if we look at the inner product, so if we let x be a vector within Tp of m, in the tangent space of m, maybe I shouldn't get too carried away with the manifolds notation. But if we take the inner product of gradient of f with x, this is just a directional derivative of the function f in the direction x. Okay, so we have a notion of a tangent plane to the surface. Okay, and then if I take a vector on the tangent plane, I essentially know that the tangent plane is actually going to be defined by this equation. So if I take a vector on the tangent plane, then the idea is that if I look at the inner product of that vector with the gradient of f, this is by definition the directional derivative of f in the direction x. Okay, but if f is if we're staying inside of the manifold, then we know that inside the manifold locally f is identically equal to 0. Okay, so f, this equation here, m is equal to f inverse of 0, tells us that f is constant and it's equal to 0 on m. Okay, so since f is just equal to 0 on the manifold m, then we know that its directional derivative in the direction x must be 0. Okay, so what this tells me is that every vector in the tangent plane to this surface, is orthogonal to the gradient of f. Okay, by definition of the surface m, because f is constant along m, and so the directional derivative of f in the direction f is 0, which tells me that two things. First of all, this is the definition of the tangent plane to the surface. It's everything orthogonal to the gradient vector of f. But that also tells me that the gradient vector of f is actually just the normal vector. Okay, so the normal vector to the surface is exactly the gradient of f. And okay, so what does this tell me? Well, this tells me that I can use the function f to define locally a normal vector field, a smoothly varying normal vector field, because f we're assuming is a smooth function, and so this gradient of f evaluated at a point P is smoothly varying locally in some neighborhood around this point, and so it's going to define a normal vector field. So we actually have an understanding not just of the normal vector at this point, but this function f gives us an understanding of the normal vector in some local region around the point. Okay? Now, let's quickly go back to the example of the sphere just to see where I'm going with this. So, if we go back to the sphere, then essentially the normal vector, so if my function f is just x squared plus y squared plus z squared minus 1, okay, and then f inverse of 0 is the unit sphere. Okay, so this is all the points such that f is equal to 0, which is the unit sphere as we previously discussed. Then gradient of f, well, this is just 2x, 2y, 2z, and this is precisely the vector which is normal to the sphere. And so we can see that immediately because this vector is in the direction x, y, z. So this is just literally 2 times the radius vector, right? It's in the direction this gradient of f is in the radial direction. Okay, so it's in the direction x, y, z. And in particular, it's the normal vector to the sphere. So this is just a nice example that shows us that what we're doing is correct, okay? So now, let's talk about the curvature. So how do we use the normal vector to understand the curvature? Well, the idea is that if we look at the derivative of the normal vector along some vector field x, we're going to be able to understand the curvature, okay? So now we need an even more detailed diagram than what I've already drawn. So let's draw a new surface. Okay. And I have my normal vector here. And then I have my tangent plane to the surface. Okay, and so here's my surface M. So the idea is that what I'm going to do is I'm going to take a vector in the tangent plane. So let's call this vector x. Now there's going to be a curve through this vector in the tangent plane. And essentially the idea is that if I slice this surface M along the plane generated by x and n. Let me get a new color now. Going through a lot of colors today. So if I look at this plane generated by the vectors n and x, and I use this plane to slice the surface, then essentially the surface is going to get sliced, like something like this, okay? So I'm slicing the surface along the plane spanned by x and n, where x is just an arbitrary vector in the tangent space. So x is an arbitrary vector in the tangent space, and n is the normal vector. If I look at the plane spanned by these two, and I slice the surface along that plane, what I get is a space curve. And not just a space curve, I get a plane curve, right? I get a plane curve that belongs to this plane spanned by n and x. And so I can understand the curvature of that plane curve, okay? Alright, so let me attempt to draw this one more time, because I want to get a good picture. Okay, so let me draw the plane first. Okay, and then let's say I have this normal vector here, and I've chosen my tangent vector to be here, and then, let's see, I have my surface. Okay, so then when I slice along this plane, I get a curve like so. Okay, yeah, that's a bit better of a picture, yeah? So, see, I have this white surface that I'm calling M. I choose a vector in the tangent plane to M, and I choose the normal vector at a point P and M, and then basically these two vectors, x and n, determine a plane, right? Their span determines this plane, which I've drawn in yellow here. And essentially, this yellow plane, which I'm kind of double bolding here, when I slice the surface M by this yellow plane, I get this, I get a plane curve, okay? And the curvature of this plane curve, okay, is going to essentially be given by the formula, which is that if I look at the directional derivative of n in the direction x, okay, then this is going to be, so if I look at the direction x in blue, I look at the directional derivative of n along the direction x. Well, x is a tangent vector to this curve, So that's precisely a generalization of the curvature of a plane curve that we discussed previously. So that's just the curvature of this plane curve. So d is the curvature of the plane curve. And the idea is that that this vector is going to be in the direction x. Okay, so it's because of what we discussed previously. If I look at the way that the normal vector changes locally, okay, if I look at maybe here's the normal vector a little bit further along the plane, okay, the normal vector is going to change locally in a direction which is orthogonal to itself, because we're assuming the normal field is a unit normal field. I should have specified that previously, but we want a unit normal field. We want this normal vector field in a patch of the surface to actually be of unit norm. So then, if I look at its directional derivative along the direction x, then the directional derivative is going to be orthogonal to the direction of n. And so in particular, it's only going to be in the direction x. It's going to be in the direction x, which is actually belongs to the tangent plane of the surface. And so if I ask for the magnitude of this directional derivative, if I ask for the magnitude of this directional derivative, it's essentially asking how much is the normal curve bending along this plane, okay? So if I have this, let's call this plane P of x. Okay, so this is the plane determined by x and n. Then the idea is that the curvature of this plane curve, okay, is essentially going to be related to how much the normal vector is bending along the curve. And so if I look at how much the normal vector bends along the curve, that's going to be the directional derivative of the normal vector field in the direction of x. And notice that this has to be in the direction of the tangent space of n. It might not be in the direction of x, but this is going to belong to the tangent plane of n. And again, it's not necessarily going to be in the direction of x, because now we have more degrees of freedom, and we'll see this in detail in the final example that I give. It's not going to be in the direction of x, but it will be orthogonal to n. So we know for certain that it's orthogonal to n, just because n is a unit normal vector. So as we discussed previously, its directional derivative in the direction x is going to be orthogonal to itself, because it's not changing magnitude, okay? And so if I define this, the inner product, if I measure the projection of this directional derivative onto the direction x, okay, and then with maybe a minus sign added here. The minus sign is just convention. It's just like a convention that we use doesn't actually change the geometry of what's happening here. And this is called the sectional curvature. And it's also denoted as a second fundamental form, okay, of x with x. And then okay, so by looking at the directional derivative of the normal vector, okay, we get a notion of the sectional curvature. We get a notion of how the normal vector is changing in this direction x. And so now we want to define something called the Gaussian curvature. And the way we're going to do that is essentially as follows. We're going to look at the maximum of this sectional curvature. So if I consider all planes which pass through this normal vector here, okay? So picture rotating this plane about the normal vector, and I'm going to have a bunch of different curves cutting out, I'm going to have a bunch of different ways to cut out curves of this surface M, and each of these curves is going to have a different sectional curvature, okay, so different local curvature at this point. And then the idea is that roughly speaking, we are looking for the K1 is going to be the maximal sectional curvature and K2 is the minimal sectional curvature. Okay, so where am I going with this? Well, the idea is that there's really there's a compact family of planes, namely for each point on the circle, there's a plane which passes through, well, for each point in the projective, for each antipodal point on the circle, there's going to be a plane passing through that antipodal point, and so there's going to be a compact family of planes that get rotated around this normal vector, okay? And so in particular, if I look at the sectional curvature of the surface M with respect to any of these planes here, then that function has a compact domain, right? It has a compact domain, and so in particular, the domain, you could think of it as just the circle, right? Any point on the circle. This circle is going to be the circle which is the unit tangent plane to this surface M. So all the vectors of unit norm on the tangent plane of M. Each vector of unit norm is going to determine a unique tangent plane with some sectional curvature. And since the circle is compact, this is actually a function with a compact domain, namely the circle, which goes into the real number. So it's going to achieve a maximum and a minimum, okay? And the maximum sectional curvature is basically the place where the surface bends the most, okay? Bends upwards the most, actually, intuitively speaking. And then, or I guess it would be downwards, right? Based on our negative sign. Yeah, because of this negative sign convention, I believe it's going to be the place where the surface curves downward the most. And then the minimal sectional curvature, on the other hand, is the place where the surface curves up the most. Okay, so if we just draw a picture of a surface here, and then, yeah, let's say that I have maybe, how do I want to draw this? Yeah, so let me try to draw a saddle for you all. So I have some sort of saddle here. I'm pretty bad at, this is hard to draw. Okay, so I have a saddle, and then this maximal sectional curvature is actually just going to be I believe it'll be the downward part of this saddle here. Okay, so that's going to be the maximal sectional curvature, and then the minimal sectional curvature is going to be the upwardmost facing curving direction of this saddle. Okay, so the direction where the saddle curves upward the most is going to be K2. And the direction where the saddle curves downward the most is going to be K1. Okay, so and then you can picture that that any plane, if I slice the saddle along an arbitrary plane here, then I'm going to have, again, some arbitrary, man, this is getting hard to draw. I'm going to have some slice of my saddle along this plane, and the idea is that the slice of the saddle along this plane is going to have some curvature, which is going to be the sectional curvature with respect to that plane. So through all the different planes which pass through the normal vector, we look at all the planes passing through the normal vector, all the curves which slice the surface along that plane, which are formed by slicing the surface along that plane, the curvature of those curves is the sectional curvature at that point, and we take the maximal sectional curvature and the minimal sectional curvature, And the interesting thing is that these quantities are not, these quantities are dependent on the embedding of the surface, but if I look at the Gaussian curvature, which is defined as the product, K1, K2, the product of the maximal and minimal sectional curvatures. This is invariant under isometry. Okay, what does this mean? Well, what this means is that somehow the Gaussian curvature, the product of the maximal and minimal sectional curvatures, is a geometric invariant where it doesn't depend on the way that this surface is embedded in three-dimensional space. Okay? So if I take this piece of paper here, and now I can embed it in three-dimensional space just as a flat piece of paper. So this could be my embedding in three-dimensional space, and the sectional curvature is going to be 0, right? The Gaussian curvature is going to be 0. In fact, the sectional curvature everywhere is 0. However, if I change the way that I embed this surface into three-dimensional space, so let's say I now bend this surface, okay? So I now have bent the piece of paper, but I haven't changed the geometry of the piece of paper. I've just embedded it differently in three-dimensional space, okay? But locally, I haven't changed its properties. I haven't torn the paper, bent the paper at all. I've simply embedded it in three-dimensional space differently. Then notice the sectional curvature is going to change because the sectional curvature, if I'm looking in the sectional curvature in this direction, right? There's actually it's curving upwards, right? So it's curving upwards, which is going to be, by this convention, a negative sectional curvature. And the point is that there's non-zero sectional curvature if I slice along this direction. But if I slice along this direction, kind of in a direction orthogonal to the blackboard here, if I slice along this direction, then notice that I still just get a line. I still just get a line when I slice a plane with this surface in this direction. So when I get a line, that's this 0 sectional curvature. And moreover, this slice is actually the minimal sectional curvature, the maximal or minimal, whichever. I think it might actually be the maximal. We're juggling a minus sign here, so forgive me if I get the minus sign mixed up. But it doesn't actually matter because it's just a convention. The point is that this slice, where we get a 0 sectional curvature, is either K1 or K2, so the product is 0. In particular, the Gaussian curvature of this embedded plane is still 0, even though I've embedded it differently into Rn. So it's invariant under isometry. So even if I bend it like this, for example, bend the paper like this, somehow the Gaussian curvature is invariant, okay? And so this is going to tell me that I can never bend this piece of paper to become a sphere without changing I can never actually bend the piece of paper into a sphere because the Gaussian curvature of a sphere is positive. So it's impossible to bend this piece of paper into a sphere because this piece of paper has Gaussian curvature of 0, and the Gaussian curvature is invariant under isometry. So this is an extremely incredible result. And then more, there's even something that's just as crazy, which is that this is still a local notion, right? We've fixed a point. We've fixed a point on the surface. We've looked at the normal vector at that point, and then we've sliced the surface through all the planes which go through that normal vector. Each of those planes will slice the surface and get a curve. That curve, the curvature of that curve at our point of consideration is the sectional curvature. And then we've looked at the minimal, maximal sectional curvatures and taken their product to get something called the Gaussian curvature, which is invariant under isometry. Now, by the way, isometry, for those of you who are more well-versed in manifolds, an isometry is a diffeomorphism that preserves the Riemannian metric. Okay, so it's a diffeomorphism, and then if I take two vectors and push them forward under that diffeomorphism, then the push forward of those vectors, their inner product will stay the same as the original inner product of the two vectors. But anyways, going back to what we were talking about, this Gaussian curvature is still a local notion because everything that we've done to get to this point, to get to the Gaussian curvature, has been fixing a point in the surface, so it's a very local notion. However, if I integrate the Gaussian curvature over the manifold, okay? If I integrate the Gaussian curvature over the manifold, I end up with a topological invariant, okay? So in particular, if I look at a sphere and I integrate the Gaussian curvature over a sphere, I end up with a multiple, think of integer multiple of 2 pi or something, a multiple of the Euler characteristic of that surface, okay? So the Euler characteristic is basically, for those of you who don't know, it comes from the theory of algebraic topology. This is a topological characteristic that's some sort of topological invariant. So it's invariant under homeomorphisms, which is a much broader class than just isometries, right? Isometries are still very structure preserving maps, but homeomorphisms are extremely they don't preserve differential structure at all. So a homeomorphism, I could take a sphere and kind of picture it as a thing of Play-Doh and just push it together and mold the sphere however I want. And as long as I don't break it in any way, as long as I don't tear that Play-Doh, that's a homeomorphism. And the idea is that if you take the integral of the Gaussian curvature over the entire surface, it's basically a fixed constant times the Euler characteristic. The Euler characteristic is invariant under homeomorphism. So in particular, the integral of the Gaussian curvature over the entire manifold, if the manifold is compact, sorry, I should specify, if the manifold is compact, which means we can integrate the Gaussian curvature over the entire manifold, then and of course that integral would be with the volume form, which is induced from the embedding into Rn, right? Or into R3. Then if we integrate the Gaussian curvature over the compact manifold, we get a topological invariant, invariant under homeomorphism, which means that, you know, really the only thing that matters is the Euler characteristic of this topological space. Now, for those of you who don't know about Euler characteristics, it's like comes from CW complexes. So the Euler characteristic of a sphere is going to be, I believe, +2. Then we have the Euler characteristic of a torus is 0. Yeah, the Euler characteristic of a sphere is 2. Euler characteristic of a torus is 0. Euler characteristic of a two-hole torus is -2. And the way you can calculate these Euler characteristics is with something called CW complexes, which are essentially like the topological skeleton of these topological manifolds. And if you understand their topological skeleton, you basically can produce this, you get the Euler characteristic, which is invariant under homeomorphism. But this is kind of going out into the weeds. If you want to learn more about the Euler characteristic, look up CW complexes, and you can study the book Algebraic Topology by Hatcher. And the point that I'm making here is that if we have a compact manifold, I've said it a million times, I'm going to say it again. You integrate the Gaussian curvature over a compact manifold, you get a homeomorphic, something that's invariant under homeomorphism, that is an integer multiple of 2 pi times the Euler characteristic of the compact surface. So you can classify surfaces. So you can classify. You can use the Gaussian curvature to actually understand the Euler characteristic, and vice versa, right? It's very. I mean, the Gaussian curvature is a local notion, but somehow when you integrate it over the entire compact manifold, somehow all of that differential structure kind of evaporates or averages out, and you just get a topological invariant. So just incredibly beautiful stuff. Incredibly beautiful stuff. And then the last thing that I'll leave you with here. All right, I know this has been a long video, and this is not a perfect video. Of course, it's not like super theoretically precise, because I'm just trying to give you some of the broad overviews of the ideas here. But I just want to share with you one last thing. So if we look at an ellipsoid, okay, this is the last example that I want to do. So if I look at the normal vector to my ellipsoid, let's actually do it over here, okay? So let's say that this is my normal vector. Let me keep the same color convention that I've been using throughout the lecture. So let's say that this is my normal vector, okay? All right, so the idea is that that if I look at planes, oh, no, this is not what the example that I wanted to give, sorry. Yeah, we're going to need to do the normal vector at the top of the ellipsoid. So take a normal vector at the top of this ellipsoid, okay? Now, if I look at how this normal vector changes, so there's basically two what we call principal directions, which are the directions with the maximal and minimal sectional curvature. The first is going to be the section with the maximal curvature. The maximal sectional curvature is going to be along this direction. Okay, so this is the principal direction of the maximal sectional curvature. And if I move along this direction, notice that that I basically am moving along some direction x in the tangent plane. Okay, the direction x is tangent to this circle. Okay, which is the circle that's kind of, if you picture the ellipsoid, it's the tightest circle around that ellipsoid. Then if you look at how if you just visualize, I want you to visualize this ellipsoid in your mind, okay? Like pause the video, just visualize this ellipsoid in your mind. Now visualize the normal vector at the top of the ellipsoid and look at the two directions with the maximal and minimal sectional curvature. So you have a circle, which is going to be the maximal sectional curvature, and then you have this large ellipse on the outer boundary, which is going to be the minimal sectional curvature, okay? And the idea is that if you look at the directional derivative of the normal vector field, the unit normal vector field, along this direction x, where now x is going to be in the principal direction of maximal curvature, notice that this directional derivative is actually in the direction of x. So the normal vector, if you just visualize rotating the normal vector around the ellipse in your mind, the normal vector is changing, actually, it's changing in the direction of x, okay? And then similarly, so this directional derivative is actually equal to some scalar multiple, which is actually negative times the maximal curvature, or the maximal principal curvature in the direction x, okay? And then similarly, if I look at x prime, and I take x prime to be the principal direction of the minimal curvature, so that's going to be like in this direction, x prime, and then I have the direction of the least curvature, which is this larger outer ellipsoid, okay? So if I go along the surface in this direction, then the normal vector is also still just changing in the direction of x prime, okay? So the normal vector is changing in the direction of x prime. So dx prime of n is equal to negative k min x. Maybe I shouldn't use x prime. Maybe let's use x naught and x1 or something. I don't want to use primes because I've been using them throughout the whole lecture. So the idea is that if I look at the direction where the ellipsoid curves the most, so that's that circle kind of the belt loop around the ellipsoid, then I get that this directional derivative of the normal vector field is in the direction of this principal direction around this circle. And then similarly, if I look at the direction of the normal vector changing alongside the outer ellipsoid, the directional derivative of the normal vector along this outer ellipsoid is still in the direction of the tangent vector which generates that outer ellipsoid, okay? So it's still in the principal direction of the minimal curvature. So in particular, the directional derivative of this linear operator called the shape operator, okay? This shape operator, which just takes in a vector x naught and spits out the directional derivative of the normal vector in the direction x naught, okay? The shape operator has eigenvectors in the principal directions of curvature. So in the direction of the most curvature and in the direction of the least curvature, the directional derivative of the normal vector stays in that direction, okay? So we call those the principal directions, okay? Now, if I were to consider an arbitrary third direction of this ellipsoid, so let's consider now a slice. This is the key. I want you to visualize all of this in your mind, okay? Without using the board. So if we could just consider another slice of this ellipsoid, which kind of picture taking an ellipsoid and slicing it along kind of a weird, not one of the obvious symmetric directions. Just slice it still with the plane through the normal vector, but now kind of in a direction that's not in the direction of the most curvature, not in the direction of the least curvature, but just kind of angled, and still passing through the normal vector. And if I look at what the normal vector is doing along this slice, then the normal vector is actually not changing in the direction of this slice, okay? So it's actually rotating. Let's see if we can, I really want to bring home this point, and then we'll call it a day. So, okay, so I have my ellipsoid, and now I've sliced it kind of in this direction here. And so if I look at what's happening along this slice, okay? So now I'm just going to draw the slice here. It's kind of like a weird random slice here. So if I look at what's happening and I visualize the normal vector as it twists along this slice, it's going to kind of twist downward almost, okay? So it's going to like, instead of just following this curve perfectly, it's going to kind of twist like almost falling towards the direction of stronger curvature, okay? So if I compare that to the direction of the maximum curvature, then the normal vector is going to stay kind of, the normal vector, of course it's going to be normal to the surface everywhere. Sorry, it should be normal to the surface everywhere. But the point is that if I look along the direction of maximum curvature, the directional derivative in this direction of the normal vector stays in that same direction of the circle. Whereas if I look at the directional derivative of the normal vector along this angled direction, then all of a sudden it's kind of, it almost gravitates towards the direction of maximal curvature more, okay? So it's not the directional derivative dx, let's say x2 now, where we've chosen x2 to be kind of a non-standard direction. x2 is the tangent vector which determines this slice of the surface. So take the directional derivative of the normal vector in the direction x2. This is not in the direction x2, okay? So only in the case of the principal direction, so only in the case that we move in the direction of the maximum curvature, or if we move in the direction of the minimum curvature, are we going to get that this directional derivative is actually this operator, which we call the shape operator, has an eigen value, an eigenvector. Okay, so if we call this shape operator L of x to be the negative directional derivative of the normal vector field in direction x, then the idea is that that L of x y, this is the second fundamental form, and L of x takes, so this is the second fundamental form, and L of x takes eigenvectors in the direction of principal of max and min curvature. So if I look at this shape operator L of x, which is essentially, I take a direction x in the tangent plane, I look at the directional derivative of the normal vector field in that direction x up to a minus sign, then the point is that the eigenvectors of this operator, it's a self-adjoint operator, its eigenvectors correspond to the maximum and minimum curvatures, okay, with eigenvalues actually given by those curvatures. And so what this tells us is that the determinant, if I take the matrix form of this, operator, the shape operator, and I look at its determinant, the determinant is the product of the eigenvalues, which is precisely the Gaussian curvature. So the determinant of this shape operator is the Gaussian curvature. And somehow this is an isometry. Okay? An isometry. Okay. All right. So thank you for listening. This was very hand-wavy. It's hard to explain this conceptually. First of all, because I'm not an expert yet. I'm far from being an expert. I'm just learning the subject myself. But I got so excited by this visualization of the ellipse that I just really wanted to share this with you all, because it was so powerful to me visualizing the case of the ellipse and then understanding that in this direction where we're not moving in a direction of maximal or minimal curvature, you can kind of visualize how the normal vector is changing, and so you can kind of see its derivative, and its derivative is not in the same direction x2. It's actually, the derivative is kind of more gravitating towards the direction of the maximal curvature. And so I just thought that this was extremely powerful, because somehow this Gaussian curvature just encodes so much information. It's such a beautiful generalization of just the curvature from calculus 1. And I just love envisioning, okay, picture the ellipse, and now picture deforming the ellipse and looking at how the curvature, the Gaussian curvature changes, right? And then the Gaussian curvature, because the Gaussian curvature is the determinant of this map, you can kind of view it as like the area formed by the two eigenvectors, okay? And so you can view it as like, so like if I were to like shrink this, let's take the direction of maximal curvature and shrink it, make it smaller, then this vector, this directional derivative of the normal vector, is actually going to increase if I make this direction of maximal curvature smaller. So if I kind of tighten the belt on the ellipse a little bit and squeeze it further along its skinny part, then essentially the directional derivative of the normal vector is going to increase, and so this is going to give us a larger determinant of this operator, the shape operator, So the determinant is going to increase, so the curvature is going to be increasing. And then similarly, if we were to expand this, this circle of the ellipsoid, this direction of maximum principal curvature, if we were to expand it, that would actually result in the directional derivative of this normal vector getting smaller, and so that would decrease the magnitude of the determinant of the shape operator. And so, because this is a local operator, this idea, if you visualize it with ellipsoids and saddles, you can also visualize it with saddles as well, then you can actually understand, like if you have a smooth enough surface, then locally it looks like some sort of ellipsoid. You can fit an ellipsoid underneath it, and basically the ellipsoid is going to be governed by the directions of the maximal and minimal curvature of your surface. And so you're going to have these principal directions of maximal and minimal sectional curvature, and those directions are going to admit an ellipse that you can kind of fit under your curvature. And so you're approximating the curvature of the surface at that point with the curvature of this ellipse. So really, if you really just meditate on this ellipsoid and saddle, the two examples, the ellipsoid and the saddle, they truly actually encode much of the more general information, because they're going to be local approximations of a surface. Yeah, okay. Thank you.